by laser. At present, wired and wireless charging methods for electric vehicles, EVs, have a number of drawbacks including short charging ranges and long charging times. Laser power transfer, LPT, is a wireless power transfer technique which can be used for UAV, unmanned aerial vehicle, and satellite charging. Recent developments in photovoltaic cells and laser technology allows the transfer power using light which might overcome many of the issues related with other charging methods. In this paper, we describe the design and implementation, in MATLAB, of a novel, high-power charging method using a laser, monochromatic light, to charge electric vehicles. The paper examines the overall efficiency of the LPT for a various input power level. In addition, it also examines the safety and the possible charging infrastructure for LPT technology. Using this technique, we believe that an overall efficiency of 10 to 37% can be achieved using existing technology. Electric vehicles, EVs, are a clean alternative to conventional liquid fuel vehicles if the electricity comes from clean energy sources. Consequently, EVs are becoming increasingly popular worldwide. However, their uptake is limited by their costs, slow charging rates, and lack of charging infrastructure. This research examines EV charging methods. Broadly speaking, there are two types of charging: wired, or plug-in, and wireless. Wired charging requires a cable to charge the EV. At present, a variety of wired charging systems exist, including Level 1, home charger, which takes typically 8 hours of charging for a full charge. Selection of laser source. There are various types of laser sources available, all of which have their own characteristics and capabilities. For LPT, laser power transfer, the available laser technologies shown in Table 1. Output power of PV cells depends on the laser intensity, W/M2. Therefore, it is a necessary factor which can be obtained from the laser flux. Solid-state lasers such as a thin disc and fiber have the advantage of good beam quality and high power transfer capabilities over long distance, but their efficiency is low. On the other hand, high-power diode lasers are not good for long range, but they are more efficient, compact, and inexpensive. This project deals with a short range, therefore laser diode is ideal for this application. For EV charging, the distance between the laser source and the PV panel is assumed to be less than 2 to 3 meters and laser is coherent beam, therefore there is a very low divergence over a small distance. In case of laser beam divergence, it can be controlled by beam guider, a device containing a beam expander optics which can control the beam divergence. Beam divergence can be measured only in the practical application as it requires to measure beam spot size and its height from the ground at the receiving and origin. Selection of photovoltaic cell. To generate an electricity from the PV, a photon's energy must be greater than the bandwidth of the PV material. There are many types of photovoltaic cells available in the market that can provide the good efficiency. Spectral response of different PV material for a various wavelength can be seen in PV cells like GaAs and C can give the highest efficiency when it is illuminated by monochromatic light at wavelength between 800 nanometers to 950 nanometers. The spectral response of GaAs can give the highest efficiency between 810 nanometers to 850 nanometers, and for C this range is 900 nanometers to 950 nanometers. However, it appears from the results that the atmospheric absorption is very high for the region of 900 nanometers to 1000 nanometers. So, C wouldn't be the best choice as a PV cell for this method, but for the wavelength 840 nanometers to 890 nanometers disturbance is very less and GaAs PV cell gives the highest output in this range. Spectral transmission data shows that there is another range available beyond 1000 nanometers which have low disturbance and it will be useful for laser transmission, but the problem with this range is that the associated PV receiver with longer wavelengths such as InGaAs, InGaP, and CIS have a low power withstand capacity. Therefore, the optimized GaAs cell has been chosen because it can withstand much higher power intensities, greater than 1000 sun. Laser safety. Since the proposal deals high-powered 10 kW laser diode, safety needs to be addressed in this project. The top 3 issues associated with the high-powered laser is addressed below. Eye safety. Here, laser operates between 810 nanometers to 850 nanometers wavelength, which is near to infrared and invisible to the human eye. Therefore, direct viewing to the laser beam and exposure to reflections can cause retina damage. Skin burning. Direct exposure to beam or reflection exposure can be led to tissue burning. Fire. A high-power laser can ignite a fire easily when the laser beam comes into the contact with a flammable material. In this approach, to avoid the unintentional shooting of the laser beam, a proximity sensor can be mounted on the transmitter and receiver end. The laser will energize the beam only when the sensors can come in contact with each other. These sensors can work as a lock and key to prevent unauthorized activation of laser. In addition, a proper laser-related precaution and rules can be implemented before their application. Simulation and analysis. the simulation has been done on a single PV cell giving efficiencies of less than 5%. The overall efficiency is low because the existing PV cell design does not operate on high power and the laser software does not produce the correct wavelength. We are in the process of increasing the range of laser intensity varies from 2W/cm2 to 5W/cm2. The results suggest that the PV cell simulation will provide 50 to 54% efficiency. Furthermore, a laser beam with wavelength of 808 nanometers, 840 nanometers, and 890 nanometers to decide the efficient wavelength for this project. In practical condition, laser shoots the beam on flat-plate PV array which contains a Gaussian beam. Therefore, power loss occurred during this operation. There are various methods available to eliminate the effect of Gaussian beam. For example, using a solar array configuration, which is low cost and doesn't require any extra components for its operation. In a solar array configuration, a various type of series parallel combination of PV cell is required to eliminate the Gaussian beam effect. It is believed that 25 to 76% efficiency can be obtained. In this approach, the electricity to laser conversion can achieve efficiencies of 25 to 76%. The current generation of PV cells can get 45 to 53% efficiency using monochromatic light. Since the lithium-ion battery can give the 99% of efficiency for charging and discharging, this technique has an overall efficiency of 10 to 37% because of the number of conversion and PV cells efficiency. Future scope. The overall efficiency that can be obtained from this technique is 10 to 37%. Improve this, we need to improve the efficiency. As the technology is improving, research will improve the efficiency of this component. Currently, most of the researchers are trying to improve the efficiency of solar cell. Therefore, there is need to improve the efficiency of PV cell and laser diode, which is specifically used for LPT. If we able to improve the efficiency of these two components to greater percentage, then this method can be used for commercial purposes. This technology can also be useful for the simultaneous transfer power and information. In this technique, a PV cell can work as a detector and receive the information in conjunction with the power beam. Laser power transfer can be an alternative of conventional charging method as it is more convenient and able to transfer high power to the receiver wirelessly. In this paper, charging electric vehicle using laser discussed here. This paper explains that the GAS PV cell is the ideal choice for LPT technology. In addition, the laser technology matched with their PV cell is also been discussed here, which shows the high power laser diode will be the good choice as a laser source. However, a laser diode and PV cell operates in 900 nanometers to 950 nanometers wavelength, which is near infrared region, and it is harmful for the human. Therefore, necessary steps were explained to increase the safety. A MATLAB-based simulation method is used for implementation of a PV cell. Using this method, it is possible that we can achieve 10 to 37% overall efficiency. There is more chances available to improve the efficiency. Researchers around the world is trying to increase the efficiency of solar cell, but the more efforts need to improve the efficiency of PV cell, which is specifically used for LPT technology, then only we will be able to improve the overall efficiency significantly. This technique has the potential of being used for long-range charging as well as simultaneously transferring power and information.